I am Guillermo Rein, and I would like to talk to you today about smouldering combustion. I wish we were all together in Naples, but this is the best that we can do in the circumstances. In the talk today, I will be telling you about what is smouldering combustion, why it is important, and how does it ignite, spread, and emit. Smouldering combustion is different than flaming combustion, the darling of the Combustion Institute. Smouldering is a slow burning process at low temperature, and it doesn't form a flame. Typically, the fuels are porous media. We will see why. The most important difference, the most important fundamental difference of smouldering combustion is that the chemistry is heterogeneous, in the sense that it involves reactants that are in different phases, namely gas and solid phases. That means that oxidation, a key step in the combustion process of the smoldering, is the molecule of oxygen has to be absorbed at the surface of the fuel, reacts with the fuel on the solid phase, and then is deabsorbed as a product of combustion. And many fuels that can sustain smoldering. Natural ones are typically wood at all its forms, peat, which is a soil that is organic, rich in carbon, that happens naturally, or litter or cold, and synthetics pretty much are all the polymer forms that we know. When we look into the characteristics that make a fuel prone to smoldering, we see that in chemical terms, there is always the presence of forming a char upon being heated, charring. This char is a porous media itself, and that actually brings physical characteristics that are important for fuels for smoldering, which is that the porosity gives the fuel a large area per volume, surface area per volume, and these areas is where the oxygen is absorbed, reacts by oxidation, and then dissolved as part of combustion. This porous nature of the fuel, it also allows oxygen to penetrate in depth. Supposed to be happening only on the face of the surface. It happens inside the material, where oxygen can actually transport by diffusion. Looking into the differences between smoldering and flaming in the chemistry side, both of them start with the degradation of the solid fuel. So if we have biomass or we have a polymer, upon being heated, it goes from the solid into a pyrrolysate gas, and also leaves behind char, which is a solid. So the process of pyrolysis leaves both a chemical component in the gas and a chemical component in the solid. Now, in the smoldering, what happens is that the char, which is a product of pyrolysis, is the one that oxidizes. The char in the solid finds oxygen in the gas phase that absorbs on the surface and burns. That's the process that releases heat, and we have CO2 and water and a very long chain of other elements, and leaves behind a solid that is ash. Whereas flaming, what it is oxidized is the product of pyrolysis that is in the gas phase, the pyrrolysate. So the pyrrolysate in the gas phase finds oxygen in the gas phase. That's homogeneous chemistry. Both of them are in the same phase, and reacts to give CO2, water, and emissions and pollutants, etc. So we see that both smoldering and flaming of a solid fuel are born out of the same step, pyrolysis, and both of them involve an oxidation. But in smoldering is the char that oxidizes, and in flaming is the pyrrolysate that oxidizes. Let me show you this video taken from the top in an experiment in the lab. This is a tray. It contains peat. Peat is an organic soil rich in carbon. We ignite it on one side, and the fire spreads horizontally over the tray. The experiment has been accelerated 600 times because the experiment takes 30 hours, whereas here I just have a few seconds to show it to you. On the left side, you have the visual camera seen from the top, and on the right side, you have the infrared. showing the differences. It actually shows you the front where the heat is being released, and you can see the shape that it develops. Smoldering has low temperature. For peat, as you see in this experiment, the peak temperature is in the order of 600 Celsius, much lower than flaming combustion. You could have coal that also smolders, and coal has the highest temperature of smoldering, which is about 1000 Celsius peak temperature for coal. The heat of combustion, the effective heat of combustion, is low. Smoldering is an incomplete process of combustion. It releases a lot of gases that still contain chemical energy that could be released by further oxidation, but it's not released. And we have about a third to a fourth of the heat of combustion of flaming in smoldering. So, for example, about 5 megajoules per kilogram. And the reaction rate, so not the reaction rate, the reaction rate as well, but the spread rate is creeping, is very, very slow. Instead of talking about meters per second or centimeters per second, we're talking about millimeters per minute. It's a very, very slow process. Typically, when someone enters into the lab here at Imperial College, they will actually say that nothing is happening. But if you come back 20 minutes later, you come back 3 hours later, you can see that the process has not necessarily moved, but over long time scales. But why do we wonder? Why do we worry about smoldering? When, in the fundamental terms, in a purely scientific terms, smoldering is a fascinating phenomena in both physics and chemistry of high complexity, and it has behavior that is very different than flaming combustion, and that's enough by itself to entice research. But from a practical point of view, smoldering is of high importance to society, to engineers, because it is the leading cause of death for fires at home. It's not the most likely fire. The most likely fire is still flaming fires, but is the most deadly fire. Why is it so deadly? Why are the burning of mattresses and sofas and upholstery and textiles, bedding, what is it so dangerous? Well, for 4 reasons. The first one is because the smoldering is very easy to ignite. It's easier to start a smoldering process than it is to start a flaming process. The second is that because it is difficult to detect. When smoldering is happening, the thermal and the chemical signature that it releases is not as obvious as that of a flame. And the third one is that the gases that smoldering produce, because they are very incomplete, they're actually much more toxic, much more lethal, and they incapacitate people who might breathe them much faster than smoke from flames. And that if that were not to be enough, smoldering can suddenly transition to flaming fire, which is much more destructive, but actually with already a size. So instead of starting a flaming fire from a small flame, it would be flaming fire that actually starts from a large area that has been smoldering. This is not just the case of basic concerns. In our homes, smoldering is also a concern in commercial airlines and even in spacecrafts because of smoldering nature that happens in this spacecraft and aircraft. Because of heat and fires, there is plenty of phones because they are light and they are good for air travel and space travel, and they have plenty of wires which provides heat and ignition sources. And these fires are equally easy to ignite, difficult to detect, toxic, and can suddenly transition to flaming. Now I want to show you a few cases, a few scary cases. The first one is that smoldering is the cause of what it is the longest burning structural fire in history. This was the World Trade Center fires that developed after the towers collapsed. It's not the terrorists took airplanes into the towers and they caused fires that actually brought 5 towers down. In the World Trade Center, it's not just 2, it's 5 towers that came down. And these are not the fires that I'm referring to. I'm referring to the fires of the debris of the towers collapse, and it creates this mountain of polymers and paper and textiles combined with concrete and steel, and these mountains of debris started to smolder. And the firefighters and the authorities of New York could not extinguish these fires, and they lasted for 5 months. You have an infrared image here, taken months after the collapse of the towers, and you can clearly see how the footprint of 3 of the towers still has hotspots, very intense hotspots, which are actually the smoldering fires happening, and all the smoke was being produced in the middle of Manhattan for many months. Very dramatic. On the natural side, although also with anthropogenic emphasis, is wildfires. The largest wildfires on Earth, in terms not of area, but in terms of volume, which volume gives you the amount of fuel that has been consumed, are smoldering. The smoldering of peatlands in particular. Peat is a type of soil that grows naturally where nature stores carbon. In 1997, this is an image of those fires by NASA. It shows you the particle matter. And the particle matter of these fires was actually started in Borneo Island in Indonesia, and going well beyond Indonesia's borders, trans-boundaries, and transcontinental. It actually reached Africa, it reached Australia, and it reached Asia, and in particular continental Asia, India, and China. These fires were absolutely enormous. The data was collected in 1997, but it was not analyzed until the year 2002. When it was analyzed, the scientists discovered that these fires of this year accounted for about 13 to 40% equivalent of the carbon emissions by humanity. This is very large. This is more than any of the vehicles in the planet. This is more than the whole of the European Union equivalent, and not accounted for, because by that time, and still, we don't even know how to count these enormous emissions of carbon emissions from peat fires. When we compare flaming fires with smoldering fires, we see how different, how this change in the chemistry leads to a complete change in absolutely everything, in the heat transfer, in the transport processes, in the fluid mechanics, in everything. On the left, you have flaming fires, flaming wildfires. The plume is very buoyant because the flame is very hot. That means the smoke is significantly hot, is significantly light. It rises up and it can reach very high up into the atmosphere. The phenomena of burning flaming fires is on the surface because that's where the vegetation, the grass, the bush, the trees are, and they move fast, relatively fast, to the point that actually it becomes a threat to safety of people that might be in the path, and they might have to be moved away and even evacuate. And the smoke is quite black, or it has a dark color, mostly because there is a significant amount of soot present in flaming fires, forest fires, because they are diffusion flames, turbulent diffusion flames. Whereas here on the right, you have what smoldering fires look like. First, the plume is not strongly buoyant, it's just weakly buoyant, because smoldering has much lower temperature, so the smoke that it produces cools down quickly, and it doesn't rise up much more than the height of a building, maybe 30 meters. So it stays on the ground where people and animals breathe, and it just moves laterally instead of moving away into the atmosphere. The smoldering process is not a surface process, it's a volumetric process. It actually burns a volume of the soil that actually is literally consumed, and it disappears, and it can be several meters high, several meters deep. And it moves in a creeping fashion, so it's relatively easy to move away from its path if you are mobile. That's not a concern as it happens in flaming fires. And the yellow has a completely different nature. It doesn't have soot, it doesn't have this dark color, it's more of organic carbon and PAH and other hydrocarbon molecules that are producing these droplets that give it a white yellowish color. When we look into the extremes of the smoldering, its ignition and its suppression, and we compare that to flaming, we see that smoldering is the most persistent type of fire on Earth. Why do we say this? Because it's the easiest to ignite. When we look into the critical heat flux that is required to ignite as fuel, we see that exactly the same fuel ignites it ignites at a much lower heat flux by smoldering, that the same source of heat has to be much higher to ignite a flame. For example, in polyurethane foam, 8 kilowatts per meter square will make it a smolder, whereas if we wanted to make it flame, we will have to go up to 15 kilowatts per meter square. That's twice the critical heat flux. Smoldering is related to some materials that have the ability to release its own heat at very low temperatures, so low that it could be ambient temperatures. This is the process of self-heating, which is very well documented in science and industry. And it means that some fuels of porous fuels, natural porous fuels of smoldering, biomass fuels, could actually self-ignite without external agents, spontaneous type of combustion at ambient temperatures, which is not far from 30 or sometimes even lower as 20 Celsius. And once they're burning, they're more difficult to suppress. They need more water. They're in about 50% more water than flaming per unit mass of fuel that is burning. And they need to lower the concentration much lower to reach that criticality where there is not enough oxygen for the oxidation to continue sustaining. In smoldering, in flaming, when we are below 16% oxygen concentration, the process stops of flaming. It stops, it's not sustaining, whereas in smoldering we can go down to 10 and sometimes even actually lower than 10%, and the process will continue. Also, the process of smothering, which is by reducing the oxygen concentration. For smoldering, we will have to smother for a very long time, sometimes actually even months if it's a natural fuel, because if we were to let the oxygen come back without waiting long enough, it will reignite. Whereas with flaming, within minutes, the fuel has cooled down enough that it will not reignite naturally by the arrival of just the oxygen. So the smoldering holding times are much, much longer for smoldering. And it's not surprising that smoldering is the most persistent type of combustion on Earth, because, for example, the oldest fire on Earth that has been continuously burning for a very long time is a coal seam that has been smoldering in Australia for the last 6,000 years at least. Some people think that actually it might have been longer than 6,000. That means that we cannot claim that the British started the fire. In this case, they have nothing to do with this. It's older than their arrival to Australia. And now this site, which is called the Burning Mountain, is a natural reserve and a native sacred site. And I recommend, if you're close to Sydney, that you stop by and you take a look at it. It's still burning. It moves about a meter per year. But how does it ignite? We can take a look at what the experiments and the modeling in the literature tells us about this. Because peat is a natural fuel. It means it's rich in carbon, but it means it has all the components in it, as it happens with biomass or with coal. Two of the components are the ones that affect its ability to ignite the most. One is the inorganic content. Inorganic content, which means minerals, means the solid material that is in the peat that would not contribute to any kind of oxidation. It will not be involved in combustion. If the amount of inorganic is too high, it will be a point where the smoldering cannot be sustained, and this fuel will not be igniting. On the other side, we also have water. Peat is formed in waterlogged conditions or in very cold conditions. It means that peat can sustain a significant amount can hold a significant amount of water. When the water table is past its location, or when it has rained a lot, it can hold actually more water than mass. It actually is a sponge in a way. And there is a point where it has so much water that it will not be able to develop a combustion process because the heat sink of the latent heat of vaporization is too high. So we put all this together. The dots are experiments in the literature conducted in Canada in 1987 that have been repeated recently. And the shadows are numerical models. And the two of them have an agreement, and they create these two boundaries, create a boundary with two regions. The region which is high inner content and high water content, where we cannot ignite, and a region where is low inorganic content and low amount of water where we can ignite. So this is the critical region, and a sample that falls within this triangle would be able to sustain smoldering, and a sample that is outside the triangle will not be able to find it. And once it ignites, it spreads. And it spreads in forming subfronts within the front of a smoldering. The most important fronts is the preheating front. So the heat that is developed from the combustion process travels mostly by conduction, but also by convection. It travels to the fuel ahead. It preheats it and it starts to dry it. So we have a drying front. Right behind the drying front, we have the sample that is dry, the biomass that is dry. It starts to increase its temperature, starts to break down chemical bonds, it starts to pyrolyze and degrade. And right behind that is the char that has been left from the pyrolysis, and it oxidizes with the arrival of oxygen, and that releases the heat. And behind is just left ash, which is the mineral content, and maybe some pieces of char that did not burn well. When we study and we quantify the spread, we obviously like it tremendously to look into one-dimensional spread, and especially also when there is a force flow, when the airflow is forced and is known. So we recognize, as it happens with flaming combustion, that there are two modes when we look into the direction of the spread respect to the direction of the air. If the two of them are in the same direction, if we are blowing air in the direction of the fire, that's forward flow. If they are opposed to each other, it's opposed flow. And what we say is that the effect of the spread rate as a function of the airflow is a very strong relationship, is in a log scale, so it's a very exponential relationship. We can increase tremendously the speed of the smoldering by blowing air on it if it's in forward flow. This is forward. Whereas if it's in opposed flow, the relationship between spread rate and airflow is weak, and actually is almost flat. And the reason for this is that the arrival of air brings two things. It brings oxygen, and smoldering is always limited by oxygen, but it also takes the heat by convection in the direction of the airflow. And in forward, that means that the heat is going to preheat the breeding fuel. That's good and accelerates the process. But in opposed flow, it means that the heat is being taken away from the breeding fuel and into the ash that is already burned. And this interplay of these two very important mechanisms of transport, oxygen transport, mass transport, and heat transport, heat losses, make forward to be accelerated, forward spread, and opposed to be hindered. And also look into one-dimensional spread, but in the vertical direction, because of natural convection, not because of force flow. There's this very nice set of experiments conducted in 1957, published in the first volume of Combustion and Flame by Palmer in the UK. He was doing piles of biomass, and he was igniting at the bottom of a pile, and he was just waiting for the fire to appear on the top. And he saw that it was very clear that the fire was always burning in the direction of the free surface. He was seeking the oxygen. So by diffusion, the arrival of oxygen was accelerating the process. And as it was getting closer to the free surface, it was accelerating. And you can see the time that it took for the fire to express itself at the top of the pile as a function of the heat, of the size of the pile. And this was very small piles, some of them 4 centimeters, but some of them were actually 100 centimeters. That's 1 meter. And take the time that it took for the big piles to appear on the top. It took them 2 weeks. This was a very long experiment, 2 weeks long, for the fire to appear at the top of the 1 meter pile. Now I want to give you a picture of smoldering as a porous reactive media. In porous reactive media, you have transport processes, you have transfer of momentum, of heat, of mass, and you also have chemical reactions, heterogeneous chemical reaction, pyrolysis, and oxidations. So you can see a little bit how they interplay together. The first one is, let's look into one-dimensional rod of fuel. We have a porous fuel. There is airflow across it in the porous media. Therefore, we're going to have transport processes of flow. We're going to have to conserve momentum. There's this flow. We will have to have continuity of the gas phase, and we will have a state law that gives a relationship between pressure and density and temperature. Then we will arrive with an ignition source, which will bring heat, and actually we will need to solve for the conservation of energy as well. So we will be tracking what happens to the enthalpy and how this energy is transported by conduction and convection and radiation, and also how heat generation, positive and negative, will be involved in the energy consumption. And then the last set of equations we will have to bring is when the chemistry starts to take place. The chemistry, the pyrolysis, and the oxidations would be affecting the composition of the domain in the solid and in the gas phase, and it will produce species that need to be tracked. So we will need to be conserving the concentration of the species in the solid and in the gas. And altogether will give us a scenario that we try to model. For example, we all have seen one-dimensional biomass rods that are smoldering in the direction of the airflow as like a cigarette, which is not a popular example, but at least everybody has seen it. This is a scenario, one-dimensional spread, that actually can be used to look into the interplay of chemistry and transport processes. These are results that I conducted for polyurethane foam, so it's not a cigarette, but it's a 1D rod of polyurethane foam ignited on one side, and then the fires are spreading in this direction, smoldering, spreading one-dimensionally in this direction. The results are computational simulations that were validated against experiments conducted by NASA inside the International Space Station in microgravity, where there is no natural flow, and the model doesn't need natural flow to give good predictions. In opposed conditions, where the fire is against the airflow, we look into the energetic release of the reactions. And when it's positive, these are oxidations, and we see that two species that are being oxidized, the foam and the beta foam. And then the negative ones are the pyrolysis. We can see there are two pyrolysis as well. Sorry, there are three reactions. The foam, the beta foam, and the char are being oxidized. And then there are two pyrolysis. The foam and the beta foam can pyrolyze. We can see that the oxidation reactions are happening on the same place as the pyrolysis. And this is why experimentalists, when they look into the behavior of opposed smoldering, they say it behaves as a one-step global reaction. Whereas if we look at what happens in forward, when we just make the air arriving from the back and aiding the spread, not only will be faster, is when we look into the structure of the front, we see that the pyrolysis reactions move ahead and they separate significantly from the pyrolysis reactions that are trailing in the back. So that's why an experimentalist, when they look into forward spread, they see this not as one step overall reaction, they see as two steps global reactions. Forward spread cannot be explained as a one step. It's at least two steps because it has pyrolysis and oxidation. And this was a nice way where a computer model was able to explain what was happening in the interplay between chemistry and transport processes. I would like to show you, and I would like to discuss with you about 4 challenges that are, as we speak, the forefront of smoldering research. There is a strong emphasis in these challenges on peat fires, being peat the largest fires on Earth. But also it happens with any type of fuel, coal or polymer foams or wood, where the smoldering is happening. The first challenge is related to the fact that smoldering is not one-dimensional in the real world. It's 2-dimensional, and sometimes actually 3-dimensional. And it doesn't happen with natural flow. Sorry, it doesn't happen with force flow, although there might be a role of wind. But they actually happen also, especially driven by natural flow, the natural flow that the same fire itself will spread. For example, when we have a bed of peat that is ignited on the top and the fire is developing, we immediately identify that there are 2 spread mechanisms which are very different in value. One is the lateral spread that happens horizontally, and the other one is the horizontal downward spread that happens in depth. When we look into these spreads in the lab, we saw interesting things. We did experiments and we tracked the lateral and the vertical spread, and we changed the moisture of the sample. And we see how the moisture of the sample affects its spread. So you can imagine that as the moisture of the sample increases, you know that is a point where the sample cannot sustain smoldering anymore. As we've seen in the previous results, there's a critical threshold beyond which it cannot ignite. So therefore, you expect that as you increase the moisture, the spread rate decreases. And that is true, but that is true for the lateral spread only. This is the lateral spread over here, the circles, and you see that as we increase the moisture content, the spread rate decreases with moisture. And there is a point where it's so wet, it actually cannot spread anymore. And that's the critical value of moisture. But from completely dry to the critical, the spread rate is decreasing with moisture. But look what happens to the downward spread. Downward spread is the dashed line over here. Downward spread, the lowest is when it's dry. And as the sample is wetter, it has more water. And this is a significant amount of more water. We're talking about 100 to 150% of water compared to the dry weight of the sample. The spread rate, the inlet spread rate increases. It does not decrease. So why does the lateral spread decrease with moisture? We know that is because of the heat sink that the water represents. It has to be evaporated. That takes heat away. That actually avoids it from going to the virgin fuel that will further accelerate the process. But why does the spread rate inlet increase with moisture? And the reason is that there is another mechanism at play here, is that once the water is driven away from the pit, what is left is a porous media with voids of space. And these voids of space, this porosity, is higher when the sample had a higher moisture content, once it has been dry. And that can be occupied by oxygen. So the higher porosity of wetter samples means that once they overcome that heat sink, they actually are responded with a faster spread, because the higher porosity means they spend less time at that location and they can move forward faster, and that the oxygen can penetrate deeper into the sample and aid the process of burning. That was an unexpected result. These results that I'm showing you of the spread rate vertically increasing with moisture content has been developed by 2 independent sets of experiments and explained as well with a computer model. So they're not controversial, but it is fascinating how little intuitive is that the moisture was going to have that effect. Second challenge is related to the transition from smoldering to flaming. So this is a fundamental problem, a very fundamental, the same way as ignition of a flame process, of a combustion process, is a fundamental problem of science that has received Nobel Prizes. The transition from smoldering, a type of combustion, into another type of combustion, flaming, is an equally fundamental, fascinating problem, where we have the smoldering, where everything is controlled in the orders of dozens of minutes, to flaming, where things are controlled by fractions of a second. And the transition between the two of them is such a drastic difference in the behavior of combustion. However, the state of the art it exists. There is a state of the art in the transition from smoldering to flaming, but it's limited and it cannot explain many things, and the number of experiments is reduced. So I'm saying this as a way of trying to bring you into solving these challenges that we have. The third challenge is related to emissions. Smoldering combustion is an incomplete type of combustion. It means that the gases that it produces are very complex, very rich in nature. There are many different components, and they have high toxicity and lethality. And this is a concern in the modern world, because these fires are happening in natural areas and they actually end up affecting people. This is, for example, the emission factors that you will see when peat is smoldering, or average behavior. You can see that the most abundant species is CO2, obviously, followed by CO, followed by particle matter. That's a completely different role to the quantity of particle matter than flaming, followed by methane and ammonia. And then you have a very long list of emissions factors. And these emissions factors are much higher than the emissions factor you will see in flaming combustion, and adds to the complexity of the process. The chemistry is very different, the chemistry of the emissions. If we look into the ratio of CO to CO2, which is a way of looking into the level of completeness, you see that smoldering is 4 times that ratio. It tells you how different it is, even when you are burning the same material, the same peat in this case. And this is important because when you have haze events, which is when this cloud is being produced at the surface by smoldering. These very fires have been burning for months. When it moves into a populated area, like for example Singapore, it actually leads to acute long-term emergency situations, because this is Marina Bay when there is actually haze. This photo was not taken when there was fog. This is not fog, this is haze. That is the smoke from thousands of cubic meters of peat that have burned in Malaysia or in Singapore or in Indonesia, and has moved into Indonesia. To the point that this is the particle matter 2.5 or smaller that we see here at the bottom in blue, because of urban pollution from the cars or from other sources that that typically and normally occur in Singapore. And this over here, 2 orders of magnitude higher, is the particle emissions 2.4 measured in Singapore during haze. This increase of 2 orders of magnitude of particle matter 2.5 is there not just for a few minutes, is there for weeks, if not months. And this is not something that you can just go into your house and forget about it. This is something that it chases absolutely everyone. It's the air that everybody is breathing. It's coming from far away, and it has moved with the wind into city and populated areas. No wonder that this leads, when there's haze events, it leads to dramatic emergencies in hospitals because of respiratory and cardiac illnesses. We're talking about 100,000 excess deaths when these haze events happen in Southeast Asia because of Indonesia, Singapore, and Malaysia. Or equal number of, for example, in 2015, they measure 140,000 respiratory illnesses and emergencies in the hospitals. And of course, we should not forget that many of these components that are in the atmosphere produced by smoldering are carbon. Peat is rich in carbon. When it burns, it actually emits a significant amount of carbon. So let me take you into this other challenge, the fourth and last challenge. It's a positive feedback mechanism with the climate between smoldering and carbon emissions. Red arrows are fire topics that I work on. Carbon emissions, when they are in excess of what the planet can actually handle, lead to changes in the radiative exchange with the sun and the space, and it leads to climate change. Climate change leads to locations to be drier soils and warmer soils, and then combustion science kicks in. If the soil, which is peat, which is a fuel, is drier and warmer, that is going to lead to even more fires and bigger fires and faster fires. So it's going to lead to more ignition of smoldering. Now, smoldering, which is of the peat. So peat is naturally capture carbon by nature, and it takes between 100 to 10,000 years for nature to grow this peat, to form this peat. Every single time it burns, the climate would not have time to adjust to us growing back or nature growing back the peat. You cannot grow the peat. When the emissions happen and within 10 years, the climate has adjusted to those emissions. And in 10 years, we cannot grow actually any peat. So every single time peat burns is a net emission to carbon. It's a carbon that nature wanted to be stored very long term, thousands of years, but it has been emitted because of the fire. This is different than flaming fires, the ones that we see in California and Australia and the Mediterranean, because they are burning vegetation on the surface. Vegetation grows fast or faster than peat. Vegetation can grow in 1, 5, 10 years. So when they burn again within 10 years, they are growing faster than the climate response to the emissions. And if we grow back the forest, we are actually making the fire that happened carbon neutral. But with the smoldering, we can't do that. So smoldering creates a positive feedback mechanism that no other wildfire produces with the climate. And this positive feedback mechanism is novel and is important, and is being investigated by atmospheric and climate experts, but they cannot do that alone because they are missing half of the feedback mechanism, which is in red, which belongs to combustion science. And we combustion scientists cannot complete this mechanism because the one that is in blue is not part of our expertise. And this is one of these cases, a multidisciplinary topic of emerging science related to climate change, of very high importance, where it requires both combustion science and atmospheric sciences together to resolve the issue, and none of the disciplines alone would be able to solve it. Okay? So with this, I'm finishing. I would just like to highlight what we have found. We have found that smoldering is the most persistent type of combustion. There is something about smoldering that planet Earth likes. That is a leading cause of fire deaths in homes. It's a deadly fire type and actually leads to the largest wildfires on Earth in terms of the volume that it actually burns. We've seen the top challenges. One of them is that the spread of these fires is multidimensional. It moves away from 1D. The transition from smoldering to flaming is a fascinating fundamental problem. Gas emissions is very complex, and we know very little about the gas emissions from smoldering compared to what we know about the emissions from flames. And then there is this feedback mechanism between smoldering combustion, and the climate. And that altogether, this represents an emerging scientific topic of global interest. And with this, I hope you've enjoyed this talk on smoldering combustion, which I typically would have served as an introduction to many of you, and I would welcome your interest, and maybe some of you want to dwell and to study the topic, and I'll be very happy to answer any question that you might have now, or you find me online, Guillermo Rein at Imperial College. I'll be happy to help you. Thank you very much.